welcome to Fermilab, the home of all things dark and mysterious. My name is Catherine, and you're joining us during our Dark Matter Day Facebook live broadcast. Today and this week on Facebook, you'll be visiting with scientists from all around the world who are searching for one of the most elusive components of our universe, dark matter. Here at Fermilab, we are 100 meters underground in an old home of an experiment called Minos. It seems appropriate to me that we use this space as our lair for learning about all the secrets of dark matter. In Greek mythology, King Minos was actually one of the judges of the dead in the underworld. At Fermilab, Minos scientists explored the universe's mysteries using neutrinos. Now, other experiments live here, including some of the ones we'll be talking about today. As we move through today's program, please feel free to like the Dark Matter Day Facebook page and share this live with your friends. Now, around 85% of the universe is still dark to us, but the jury's still out on what dark matter actually is. To wrap our heads around this, we have Dan. Hi, Dan.
Hi, Catherine. So let me tell you a little bit about why we think there is dark matter. When we look out into the universe, we see things like this where there are clusters of galaxies colliding, and the normal matter, the stars and gas, interact as the clusters go by and heat up. It's these pink spots, but there's something else that's passed right through and is exerting gravity, but not showing any light, not producing light, not absorbing light, only gravitationally interacting. That's what we call dark matter. The name might be unfortunate. You might think it should be called invisible matter, but dark matter is the name that's stuck since this was first understood. Now, I said it's out here in clusters of galaxies, but it's also in our own Milky Way galaxy. So the Milky Way galaxy that we know and love is this band with a bright core and stars and a disk. But when we look at the stars rotating on the outskirts of this galaxy, of our galaxy, we find they're rotating way too fast for the gravity exerted by the material that we can see. So there's some other material, dark matter, that's a halo encompassing our galaxy that's holding our galaxy together. And in fact, it was responsible for forming our galaxy in the first place. So dark matter is why we're here, because it drew all the normal matter into the structures we see. So that's the evidence for dark matter. It's just gravity and looking out in telescopes in space. But we would like to know more about what dark matter is.
So Dan, if we could actually see dark matter, what would it look like?
That's a really good question, and the honest answer is we don't know, but our best hypothesis is that dark matter is a form of elementary particle that's not the sort of particles that make up you and I, but something else. But we don't know anything about the mass of this particle, and in fact it could encompass an enormous range. So to illustrate that, this poster shows you the range of possible dark matter candidates. These are physics units here, which you can ignore, but we've made a correspondence with real world things. So there's viruses, bacteria, bugs, basketballs, Michael Jordan, all the way up to the Hoover Dam and Lake Michigan, and ultimately to black holes. That's an enormous range of masses, and the range of masses for dark matter particles spans very much that same sort of span, although obviously much smaller masses than we're talking about for normal matter particles. So how would we go about detecting such particles? That's why we're down here, because many of the experiments that you're going to hear about from my colleagues today require some shielding from other particles from space called cosmic rays, which are not dark matter, they're normal matter, but they constitute a background that would be hard to see dark matter beyond the cosmic rays. So we come down here and let all of the rock above us absorb most of the cosmic rays, and then if there's dark matter, we should be able to see it with some of the types of detectors you're going to hear about. And the detectors you're going to hear about are now trying to span most of this mass range that we're showing here.
Thanks very much, Dan.
Sure.
For those of you who are just joining us, my name is Catherine, and we're embarking with Fermilab scientists on a spectacular dark matter day happening all around the world. You can like the Dark Matter Day Facebook page, and you can also share the hashtag Dark Matter Day. Dan just told us what we think dark matter particles are and why they're there. But how do we know if dark matter actually exists? Turns out there's all sorts of cool experiments going on at Fermilab just to figure out what dark matter would look like. And the first experiment we'll be talking about is Nexus, and for that we have Noah.
Hi, Catherine. So the first experiment we're going to show you is Nexus, which is in this big clean room, and we'll be going in here in a minute. But first, to explain how we detect the type of dark matter we're looking for, we have this little model of a crystal. So we use ultra-cold silicon and germanium crystals, and the idea is when these crystals are very hot, they're a very regular set of atoms and bonds between atoms, and so when they're heated up, they vibrate. As you cool them down, the vibrations slow, and when we get to thousandths of a degree above absolute zero, there's virtually no motion. And when we want to look for a relatively light dark matter particle, we're actually looking for something like this ping pong ball to bounce off one of these bonds and create a tiny little excitation. And so this little vibration is something we can read out with our very sensitive electronics that also operate at these very cold temperatures. So I can take you guys in to come see my setup.
Let's do it.
We'll tell you a little bit about it. So welcome, you're entering the Nexus clean room. So a clean room, it just has this flow of air as a vertical sheet that takes all the particulates out of the air and pumps them out the vents in the side of the room. If you look over here, this is our fridge. So it's a fridge just like you have in your kitchen, except instead of getting down to like where water freezes, we get down to fractions of a degree above absolute zero. So right in this region, here, we have our little experiment. I'll show you that detector that we have in here in a second. Not the same one, but an exact copy. Right here is 13 thousandths of a degree above absolute zero. It's surrounded by a couple shields that are at different descending temperatures. And again, I'll show you actually what the status of those are. An outer vacuum vessel, and then this blanket here that you can see, which is a special material designed to repel magnetic fields. So at the center of this volume, if you could see it, you'd see a tiny little detector surrounded by all of these layers of copper and aluminum and magnetic material and even lead that shield it from light and from radiation and from magnetic fields. So it's a very sensitive, ultra-quiet environment in here. We're in this big clean room underground where we're shielded from cosmic rays and from lots of extra electrical signals like Wi-Fi and AM radio. So this is a really great place to do science. So if you want to come over here, I can actually show you a little bit about what we're doing and sort of draw some analogies to temperatures you're used to. So if we look here, this is a temperature scale going from things you deal with in your kitchen to the stuff that we can only do in these very expensive, fancy refrigerators. So if water boils at 212, and this says today's high temperature is 77. I wish it was 77. It was 34 when I got here. So we're actually closer to water freezes upstairs. But you know, typical Chicago winter, I remember February got down to -20. That was a tough day. South Pole, where some of our colleagues go. But you need to go all the way to -495 to get to where SuperCDMS and Nexus operate. So this is very, very cold. It's not like any temperature that you've ever experienced. And the centers of these experiments are actually some of the coldest places on Earth. So we're live streaming to you from one of the coldest places, definitely in Illinois, and probably on the planet. So I can actually show you the status of our experiment. So this display is what we use to control the cryogenic, the cooling aspect of our experiment. Has a little model here, and just like your fridge at home, it uses compressed gases to take a hot part and a cold part of the fridge and separate them in temperature. So outside is 300 Kelvin. We have the top of the fridge is 65 Kelvin, and it goes down in stages. So the next stage here is 3 Kelvin. It's where helium-4 liquefies. And then we have a second stage, which is around 1 Kelvin, which is where helium-3, which is a special type of helium with one fewer neutron, it liquefies at a colder temperature. And we mix those two together, and the heat of that interaction allows them to cool down the bottom here to about 14 thousandths of a degree above absolute zero. So this is a real-time readout, and we have this diagram, which I won't go through in detail, but basically showing us how things flow and letting us open and close valves and turn off pumps and all that stuff. So we're doing all of this to cool our detectors. And what we run here are very small sensitive detectors to look for light dark matter. So I actually have, this is an exact copy of what we have in there right now. And so these are silicon chips. And so what you see is it's about a gram silicon rectangle. On the top are these superconducting sensors. And so they are the things that actually read out those very small vibrations. We sandwich that crystal between these two circuit boards. These are just normal circuit boards like you'd see in your computer. We order them from the same company. But they have wires on them that also go superconducting. So this is all electronics that are meant to work at these very cold temperatures. And we apply sort of an electric field across this thing to drift charges. And with the readout we have, we can actually see 1 electron versus 2 electrons versus 3 electrons in these detectors. And that's really what we need to see in order to search for dark matter. So this goes in the center of the experiment. And we use our very sensitive electronics to look at those very small signals. And from there, it's really about minimizing noise and understanding our environment and really making sure that our sensors perform the way we expect them to.
Now, Noah, I also heard Nexus celebrated an achievement recently. Could you tell us about that?
Yeah, so for the first time, actually on Monday, we got to this very cold temperature with a working detector in the fridge with all of the readout electronics set up and the entire facility operational. My assistant Corey, who you might have seen in the background, he's a grad student visiting from University of Florida. He was actually just playing with some of these electronics where we actually are looking directly at signals, sort of a test signal on the detector, and we actually expect to start doing science right here, looking for dark matter and setting world-leading limits in the next month. We might even start in a couple days to see our first calibration signal. So it's a very exciting time for us.
Thanks, Noah. That's some very cool stuff.
Thanks, Catherine.
Let's turn to Shravan, who's going to tell us about SENSEI. Hi, Shravan. I'm guessing SENSEI doesn't mean a martial arts teacher, right?
No, it doesn't. So in experiments like SENSEI and DAMIC, we use things called charged coupled devices, or CCDs. Now, people use these every day in their phones and digital cameras such as these, if you look closely in there. Now, the way that this camera works is that photons interact with the electrons of the CCD and excite them. The detector measures these electrons and produces an image from that you can post on Instagram or Facebook. Now, in SENSEI, we don't post our pictures to Instagram or Facebook, and we use much more massive CCDs. So if you compare the size of these two, this is almost like 100 times as large. In addition to using larger CCDs, we also place our CCDs in copper housing such as this. If I could get it in. Now, we go deep underground to prevent cosmic rays, but some cosmic rays still get through. And this copper is very good at absorbing cosmic rays so that it doesn't interact with the CCD itself. In addition to this, we also cool the copper down to a very cold temperature so that we don't get noise from the thermal fluctuations. And here is an example of a picture we took underground. Now, if you look here, the things that look like little worms or snakes here are cosmic rays, and that's because we're not deep enough underground yet. And in the future, we're taking our experiment deeper underground in SnowLab, which we'll explain to you later.
Thanks, Shravan.
Yes.
Now, Mariano is going to tell us a bit about SENSEI's experimental setup.
Hey, how are you?
Hi,
Thank you for
good.
coming in.
Thanks.
I'm Mariano. I'm a PhD visiting scientist from University of Buenos Aires, Argentina. Please come on in. Okay, so here is SENSEI 10. Here we have our computer where we take our data from our electronics. Over here we have a bunch of rack of electronics. And over here we have our experiment. This is a vacuum chamber, which is, as Herman has said, at 140 kelvins. Here we have our electronics which connect with the rack where we can get the data. We have our pressure measure and everything. And the CCD is about here. Right now, we are at the point where we can actually measure. I mean, we're very good at measuring one electron signals, which means we are very good at making decouple the dark matter from everything else, exotic signals and from background radiation or cosmic ray. And right now we are at the point we measure one electron per pixel per 3 years, so we need to go to deep underground to do this.
Sure. And I heard you're deploying one of your detectors soon at SNOLAB.
Right, thank you. Yeah, we are planning to deploy an experiment. The same experiment is SNOLAB, which is 2,300 meters below ground, which is like 1.5 miles. Yeah. Mm-hmm. So this is happening maybe in a few months. So yeah, that's it.
Very cool.
Yeah, thank you.
Thank you.
Thank you, guys.
Another experiment at SNOLAB, the SuperCDMS experiment, will also be starting up in a few years. And to tell us about that, we have Lauren.
So I'm Lauren, and I work on SuperCDMS with Dan and Noah. And so SuperCDMS is also another experiment looking for dark matter. SuperCDMS, unlike SENSEI and Nexus, is looking for dark matter that's a little bit heavier, more massive. Because, as Dan said, we don't really know how massive dark matter is, so we sort of have to have experiments that cover a range of different possibilities. So, similar to Nexus, SuperCDMS is using crystals to potentially detect dark matter, and we are also looking for the tiny vibrations caused by dark matter interacting with the crystal lattice. So, to give you an idea of what that would look like, let's go back to our crystal lattice model with the ball and spring. And so now here I have a dark matter particle, but it's heavier than the previous model. And so let's see what happens when it interacts with our lattice. And so if you remember Noah's demonstration, you might remember that the lattice did not shake as much because the ping pong ball is light, but our heavy particle makes it shake much more. And so what that means is that we have a larger signal to detect. And so that potentially makes it an easier situation for us because we have a bigger signal in terms of the amplitude that we see. However, there are things that make it potentially harder. And so one of the issues with dark matter being heavier is that there are fewer of them out there. And that means we would expect much more rare interactions compared to a light dark matter particle. And so that presents several challenges. One of which, so the ways in which SuperCDMS tries to address these is to, for example, have much bigger detectors. And so this is an example of a SuperCDMS detector. The ones we are building for our next experiment are actually even bigger than this. And if you compare this to the SENSEI and the Nexus detectors, you can see that this is a much bigger detector. For example, it's much thicker. And also the air, it's much larger in diameter. So this poster also shows you a picture of our detectors. The other thing that SuperCDMS will do is go underground to a very deep underground location. So where we are right now is at Fermilab in the neutrino experimental hall, and we're about 100 meters underground. SuperCDMS will be operating at SNOLAB, which is actually 2,000 meters underground, and it's located in Canada. And if you can see this picture, it's just a little diagram that shows you how deep SNOLAB is compared to the surface. And so the reason why we do this is because it reduces the flux of cosmic ray particles, and so cosmic rays produce a lot of background for our experiments. And so we go to this extreme measure of building our dark matter detector 2 kilometers underground in order to reduce, in order to use the Earth essentially as a shield from those background particles. So SNOLAB itself is a clean room, so you went inside of the clean room for Nexus. As an example, the entire lab of SNOLAB underground is a clean room, and so that again reduces a type of potential source of background for SuperCDMS, which is radioactivity. And so most dirt and common contaminants contain trace amounts of radioactivity. And so in addition to that, we also have to build a large amount of shielding around our detectors once we are 2 kilometers underground. And so this diagram shows you the schematic for SuperCDMS. And so our detectors, which I showed you a model of, in this picture are these very small structures here. And I forgot to mention that we will have 24 of these in SuperCDMS in an array. And so that's this array here. And what you can see is there's many tons of lead and polyethylene and copper shielding surrounding our detectors. And then we also have a dilution refrigerator to cool our detectors down to 3 hundredths of a degree above absolute zero. So this plot here shows you our scientists' prediction of the sensitivity for the experiment. It's actually being constructed right now. It's an international experiment with 25 different institutions on it, and Fermilab is one of them. And so all of these different institutions from around the world, they each build a piece of the experiment, and then we put it together underground at SNOLab. And so we're expecting to have data in about 2 years from now, and so hopefully you can hear some nice results from us then. So thanks, Catherine.
Thanks, Lauren. We'll look for results in 2022. Now, last but not least, we have the Axions. For that, we have Raksha.
Thank you, Catherine. Hi. Hi, everybody. So you guys probably heard a lot about WIMP's dark matter up until now, which are much heavier than the type of dark matter that I'm going to talk about today. So the type of dark matter that I'm going to talk about today is very, very light, like ultra light dark matter, and it's called Axion. So I'll first talk to you about a little bit of intro on how to detect these axions before I move on to a couple of experiments that we do here at Fermilab to look for these. So we are the technology that we use to detect these axions is very different than the WIMP's sources that you already heard from my colleagues earlier. So these WIMPs, as you already know from Dan and Noah's talk, that they scatter like billiard balls in your detector. Whereas these axions, we kind of think of them as these waves of particles coming and drifting to our detectors and apparatus. And so imagine like football stadium size waves of these tiny particles drifting through your experimental apparatus. So these particles convert into photons in the presence of a very strong magnetic field. So almost all the Axion experiments need very strong magnetic field. And so one common thing between all this is, so you might say, you know, we have these photons as signals coming from this dark matter, but we have photons everywhere. So how do we isolate these signals from our background, right? So that's a very valid question. So in order to do that, we do our experiments in cryogenic environment, meaning we do them in a refrigerator, in a closed environment. So that's also another common factor between all these different Axion experiments. So I'm going to show you this couple of experiments that we are involved in at Fermilab here. So the first one is called Axion Dark Matter Experiment. In short, it's called ADMX. And so since I can't take you on a tour of actual lab, which is located at University of Washington in Seattle, I'm going to just give you a virtual tour through these pictures. So here is the detector that's hanging in this clean room over here, where all the electronics and everything goes in. And so here is a pit, and underground is a magnet, 8 Tesla magnet, where this detector goes in, and we do the data taking and everything. So the experiment is located underground here inside this pit. So the detector looks like this. To give you an idea of how it looks in comparison to humans, you can see it's about 10 to 12 feet tall. And here is the inside of the detector. So the axions convert into photons in this region where there is this uniform magnetic field. And these antennas pick up this very small signal coming from the dark matter, and they send it to this quantum amplifier package, which amplifies this dark matter signal without adding too much background noise photons themselves. And the main idea is everything happens in this refrigerator environment. So we cool everything down very, very close to absolute zero, thousands of a degree above absolute zero. These are not your typical kitchen refrigerators. So that's basic idea behind Axion detection. So I'm going to play you a video here that shows the detector, but I also have this mock over here. So the main part of the detector looks like this, where the electronics are housed on this hexagonal surface here, and the inside has these quantum amplifiers. I'll show you in a bit how that looks. So basically, this part is actually fabricated and designed at Fermilab here, and we just delivered one of these for the run that's happening right about now. And so it's taking data with this hardware that we designed and fabricated here. And we have already taken a couple of runs worth of data with the hardware. So here is a picture and a small video of the detector core that I just showed. So this is an actual detector where all the electronics are housed, as you can see. And the inside opens up, and it has the quantum amplifiers, and it's shielded inside in this mu metal shield that shields it from the ambient magnetic field, because these quantum amplifiers are delicate and they get destroyed in the magnetic field. So these are the quantum amplifiers. So this is one of the main technologies that we use for Axion detector. So before I move on to this another experiment, I want to mention that we have achieved really nice, interesting results recently in ADMX, Axion dark matter experiment. We are in the process of publishing our results in this really major peer-reviewed journal. So if you are interested, stay tuned for that. And I want to mention ADMX is the most sensitive Axion dark matter experiment in the world. So I will move on to the second experiment that we are involved in here at Fermilab. So this uses different technique. Obviously, it also looks for Axion dark matter. This uses something called artificial atoms or qubits. Many people have probably heard of qubits in the context of quantum computers. So basically what these artificial atoms are they are two-level system, meaning they have ground state and excited state. So turns out you can actually tweak the energy gap between this ground and excited state to match to the dark matter that you want to see, the energy of the dark matter you want to see. So the basic idea is when the dark matter hits your detector, the number of dark matter corresponds to number of photons that you see, and these photons actually excite the artificial atom. So that's the basic idea behind this experiment. So the experiment is obviously located in a refrigerator, like I mentioned earlier. This cools everything down very close to absolute zero. So this gold-plated part is the dilution refrigerator. And so the artificial atom is located in this shield, magnetic shield over here, and all the readout electronics and everything are distributed in the different fridge area. So right now we are trying to read multiple artificial atoms simultaneously in this refrigerator at Fermilab. So the ultimate plan is to have sometimes next year or so a 14 Tesla magnet that will allow us to convert this Axion dark matter into photons in our laboratory using this experiment, and sometimes after that we should be able to take some science data. So that's kind of the plan with this experiment, and so that's kind of the summary of the two experiments that we are involved in here at Fermilab that look for Axion dark matter.
Thanks very much, Raksha. Now, if you're just joining us, you've missed a bit of the presentation about what dark matter is and the experiments that are going on at Fermilab to discover it. But never fear, you still have an opportunity to submit your questions, and we'd actually like to go over some of those now. So if you'll follow me. Hi, everyone. So the first question that we have today is, could dark matter have played a role in the matter-antimatter symmetry in the universe?
Anybody want to answer that? The honest answer is we don't know. Some theoretical models suggest that it could have, but until we actually detect dark matter and understand what type of particle it is, we won't know the answer to that question.
And I believe I also saw a question about the kind of like the mass range, the range of masses that we're talking about for these different particles. We talked a lot about those today.
Yeah, so I guess Dan already covered this earlier. So as you saw in this chart over there earlier that Dan showed, it can be ultralight to, there have been some theoretical models where even medium-sized black holes could be dark matter candidates. So it does indeed span a wide variety of masses.
Sure. And how do you get signal out from these superconducting detectors?
So the general scheme is usually we put a current through one of these superconductors, and because a superconductor is this material that at a very specific temperature rises or falls in resistance, any little signal is a big resistance change. And Ohm's law, which says the voltage across something is the current times the resistance, if you have a fixed current and a very changing resistance, you have a very changing voltage, and that's what comes out of our cryogenic environment. So what's in there are some very sensitive amplifiers to make sure we can read a very small voltage that's in the cold part to a larger voltage in the warm part, but that's essentially the entire principle, and we exploit that property of superconductors to read out very small signals.
Sure. And is dark matter out only in space, or is it everywhere?
So I think Dan may have touched on this also initially. So we believe that dark matter is essentially a cloud that the galaxy is rotating through, and so that would mean that dark matter is moving through us, and it's it's ambient. So in terms of outer space, it is outside of the Earth's atmosphere, but it's also moving through us. So dark matter forms the structure of the universe, and so it's everywhere.
And just in terms of like how you kind of go about making these experiments, how do you generate testable hypotheses when what you're looking for is so elusive?
So we have to use very clever techniques. Like in the context of like Axion, for example, like you need specific conditions, like for example the high magnetic field, otherwise you wouldn't be able to see it, and then there are ways of integrating for a really long time for the signal, otherwise you are not able to see this extremely small signal. So there are very clever ideas and ways that we borrow from atomic physics and other areas of physics that we implement to look for these dark matter particles.
And what's the relationship between dark matter and dark energy? Sorry, we're kind of switching between theory and experiment here, but...
So from a historical perspective, dark matter and dark energy, these are both things that we inferred from looking at the universe and seeing how things move. And the real difference is it's in scale. So dark matter is something we see at the galaxy scale, and so we watch how stars move in a galaxy, and we infer that there must be a lot more matter there than just in the stars and gas. Dark energy is something you only see beyond like the cluster scale, and so if you look at groups of galaxies over much larger distances, it's the thing that seems to be pushing them apart further than they should otherwise be moving apart. So they both have something to do with general relativity, but dark matter fits much better as a new type of matter, whereas dark energy is much closer to something intrinsic to space-time itself. We work very closely with people who study dark energy, and actually the CCDs that the SENSEI people use came from CCDs developed for the Dark Energy Survey, which is also an experiment running partially out of Fermilab. And so a lot of the overlap experimentally is very close, even though maybe the science itself, what we actually look for, is very different.
This next question is maybe for several of you. What's the coolest result you expect to see in the next few years?
You guys want to take it?
The coolest result you want to see ever?
The coolest result for SENSEI would be that we find all the dark matter particles, and tomorrow or today would be really cool. A different experiment.
So for ADMX, we are, as I mentioned earlier, the most sensitive experiment looking for Axion dark matter. And when we are taking data, we are in the sensitivity regime that we can detect the Axion anytime if it exists in the range we are looking in. So yeah, it could be very well that we can discover this in the next couple of years.
And also, it's very important to know that every result is a good result right now, because we will know and we will learn more about dark matter and its own nature.
One of the cool things about this is we're all working on different experiments. So SENSEI and Nexus and SuperCDMS are looking for very much the same thing. So we compete, but we also cooperate. We're working at the same lab. We use some of the same technologies. We have many of the same problems in reading out our detectors. So it's nice to be here together to share that knowledge.
Do you have cosmic ray detectors that can be used as a veto for your dark matter signal?
So that's an interesting question, and the answer is yes. And in fact, we do often implement cosmic ray detectors that we use to veto backgrounds. It turns out that the answer to this question is a little more subtle than that, in that there's two components of a background that's produced by cosmic rays. One is from the cosmic ray essentially going through your detector, which then you can use the veto in order to reject that. But in another case, the cosmic ray goes through material near your detector, maybe in the cavern wall, or maybe in above, in the material of your shielding, where you may not be able to instrument everything with cosmic ray vetoes. And in that case, there's still particles that are produced that can travel and hit your detector and produce a background. So it does help to have it, but ultimately we need to go to a very deep location in order to reduce all of the backgrounds associated from cosmic rays.
Thanks, Lauren. And that kind of transitions into our next question, more of like a day in the life sort of thing. What's it like working underground for so much of your day for those people that do?
I can go down the line.
Well, I'll start. I mean, we worked underground with SuperCDMS in northern Minnesota for a dozen years. And at this time of year, you go underground in the dark and you come up above ground in the dark. You don't see the sun for quite a while when you're working on the experiment. But when you're actually underground, it's much like the lab you see here. It's a generally well-lit cavern with at least some of the amenities that you would like to have. And you're spending your day as if you were in the lab at Fermilab. You're only really aware of coming above ground, of course, at the end of the day when you get in the elevator and come up.
Yeah, I haven't spent as many of my years underground as Dan has. I'm on the other side. But yeah, I think this environment is actually really unique, since we can come underground, get some of the same benefit from the rock, and I can still go up and get a sandwich at Subway or something for lunch and come back down in the afternoon. Whereas Sudan was a day thing, and where we're going next, Snow Lab, is actually a clean room underground, and that's even more investment of changing your clothes, and you can't bring in your cell phone and everything. So it varies. It's interesting. It does become sort of normal after a while, in a way. So we had a ping pong table in the Sudan mine, and so you'd go down and you'd have your coffee, and you'd go do the thing in the clean room, and you'd play ping pong, and you'd get tired. And you'd see a bat, so that was a little different. But otherwise, it was like a normal work day, and you'd be tired at the end of the day, and you'd go home and have dinner. So, yeah.
Sorry. I only get to work in the basement without windows.
So, yeah, I think all the things that everyone has said are definitely true. I think for me, one of the things is working underground requires a little bit more organization than you might be used to working above ground, especially at a place like Snow Lab or Sudan. Though here, if you forget something, it's not too hard to go back up. But, you know, as Noah said, at SNOLAB, for example, you have to take a shower once you get down there, and there's really only one ride down in the morning and one ride up, and you have to be there, you have to be on time, and you have to have everything that you need with you during the day.
So I haven't been working here as long as these other people, but I still think it's really cool to come down here every time I come here. And I'm like half a mile underground right now, and that's really cool. That's all I have to say.
Yeah, I think that's it. I mean, it was a little weird at the first time, but now it's like a common day-to-day thing. Yeah.
Thanks, everyone. This seems like a great place to wrap up. I'd like to thank all of our scientists here for coming to us today and telling us about all the cool things that they do. I know it was a real treat for me, and I hope it was a real treat for all of you at home. I'd like to say thanks again. Like the Dark Matter Day page on Facebook and on Twitter. Be sure to share this video. You should be able to find it online later. And remember, don't be afraid of the dark.